Hi everybody, welcome back to this course on Internet Technologies. I'm Vardan and today we'll be studying about Transport Layer Security or TLS protocol. So TLS or Transport Layer Security is a cryptographic protocol that ensures secure communication across networks like the Internet. It's the successor of SSL, which we learned in last lesson, and it's now deprecated due to known vulnerabilities. TLS operates at the transport layer, meaning it secures communication without having to look inside application packets. This makes it efficient and non-intrusive to the underlying data. The most visible part of TLS is in HTTPS, where it safeguards websites, ensuring your interactions are encrypted and private. TLS also plays a role in secure email, SMTP, VPNs, and instant messaging services. The protocol has evolved over time, and TLS 1.3 is the most recent version, and it offers significant security and performance improvements over its predecessors. Now, TLS, like SSL, is built around multiple sub-protocols, each designed for a specific role in securing communication. First, we have the TLS handshake protocol, which is responsible for initiating the connection and negotiating the session keys and cipher suites. Then the TLS record protocol provides the main functionality of securing and transmitting the application data. This includes encryption, integrity verification, and fragmentation. There's also the TLS alert protocol, which is used for error reporting. Say if there's a failed certificate verification or a session needs to be terminated. And then change cipher spec protocol is finally used to switch from unencrypted to encrypted communication, although it's removed in TLS 1.3 as we'll see later. Finally, the application data protocols like HTTP, SMTP sit on top and rely on TLS rules defined by the record protocol to secure their messages. The TLS handshake, just like the SSL handshake, is the heart of the secure connection setup. It begins with the client hello message. This includes the TLS version the client supports, a list of cipher suites it can handle, and a random number which will contribute to key generation. The server then responds with a server hello message. It supports one cipher suite and it chooses one from the list that the client gave, and it then sends a digital certificate containing its public key, its own random number, and then a session ID. The client then validates the server's certificate, typically using a certificate authority. If valid, the handshake continues. Now, a symmetric key needs to be exchanged. This can happen through RSA encryption. Client encrypts a pre-master secret and server's public key, or through Diffie-Hellman exchange. In TLS 1.3, static RSA is deprecated and ephemeral Diffie-Hellman is preferred for stronger security. Once keys are derived, both the client and server find a finished message using the newly agreed encryption. At this point, the secure channel is established. Once the handshake is completed, data transfer begins over a secure and encrypted channel. TLS typically uses symmetric encryption algorithms like AES, which are both fast and secure. To maintain data integrity, TLS uses a message authentication code or MAC attached to each record. This ensures that even if someone intercepts the message, they can't tamper with it. A modern approach called AEAD, that is authenticated encryption with associated data, is used in TLS 1.3. It combines encryption and authentication in a single step. It protects both the message content and metadata like sequence numbers or protocol parameters, making sure that the attacker can't even see how the protocol is functioning, let alone the content. When the session is to be closed, either party can send a close notify alert, which is essentially a clean shutdown of the TLS session. TLS 1.3 introduced several key changes that simplify and strengthen the protocol. The change cipher spec message is now removed. As soon as the handshake ends, encryption may start immediately. Also gone are the static RSA and static Diffie-Hellman for key exchange. They've been replaced by ephemeral methods like elliptic curve Diffie-Hellman ephemeral, which generate fresh key pairs for every session, providing forward secrecy. Let's now understand what a cipher suite is. We've been talking about a cipher suite a lot. So a cipher suite is basically let's say a recipe for how encryption, authentication and key exchange will be performed. For example, TLS AES 128 GCM SHA-256. It means use TLS protocol, use AES with 128-bit key, GCM mode of encryption, which is a type of AEAD, then use SHA-256 as the hashing algorithm for integrity. These suites are designed to balance performance with strong cryptography, and they are selected during the TLS handshake. With that, we've come to the end of this video, and the next video will be about SSH and IPsec. So thank you for joining in, and I'll see you next time.